All right, we will begin our discussion of the cardiovascular system, and this includes talking about the blood, heart physiology, and blood vessel physiology. So we're going to start off with blood. We did talk about this in lab in terms of the components of blood and what percent of blood is plasma, so we're not going to revisit those topics. We're just going to continue on with the physiology of blood. So when you think of what the functions of blood are, it's transporting gases, nutrients, waste products. For example, the important gases transported by blood are carbon dioxide, which is a waste gas as a result of metabolism, and oxygen is something we need to fuel our cells to make ATP. So gases, carbon dioxide and oxygen are the two that are important. And are transported by the blood. Nutrients, an important nutrient is glucose, and there are others as well as proteins, fats, other carbohydrates, but glucose being the primary nutrient for our cells. And waste products such as urea, which is a waste product as a result of breaking down proteins, and there's other waste products as well. Processed molecules, these molecules may be substances that are changed as they are circulated throughout our body. For example, vitamin D, which is made in our skin, it is sent to the liver and it's modified a little bit more, then it's sent to the kidneys, which modifies a little bit more into its final form, which is vitamin D3 that we secrete into our small intestine to help us absorb calcium. Regulatory molecules, examples of that would be like hormones. Hormones that are secreted by the different endocrine organs regulate activity of certain organs, so those are important, and those are transported by the blood. The blood is also an important regulator of our pH. We have a very narrow pH range for our blood, and that is 7.35 to 7.45 is the normal pH, and we have buffers present in our blood that help to absorb minor changes in pH. If we become too basic or too acidic, these buffers act to regulate that pH and bring it back into that normal range again of 7.35 to 7.45. Osmosis is the movement of water in and out of our blood from our tissues, and also then into our kidneys for making urine. And there are factors in our blood that help determine how much osmosis occurs. Things like the amount of solutes in our blood helps to influence osmosis, as well as the amount of protein we have in our blood also influences osmosis. And you'll learn more about the details of that when you get into general A&P or if you have to take advanced A&P. Maintaining body temperature, we'll find that the largest blood vessels are in the core of our body, and that's what holds most of our body heat, is in the core. And we also know that muscles contribute to body temperature as well, but our blood is a slightly higher temperature than our general, surface body temperature, because it's down in the core and where our largest vessels are. So when we need to quickly raise body temperature, we, give, warmed blood, or if you need to cool body temperature, we can give, cold fluids to help bring body temperature down. Protection against foreign substances, that includes the white blood cells that we find in the buffy coat when we separate out the components of our blood. So we produce antibodies, and those are also found in the plasma. So antibodies in the plasma, white blood cells in the buffy coat, those all help protect us from foreign substances. And also we have clotting factors that stop bleeding and protect from infection when we tear our tissues or our blood vessels. And again, clot formation helps stop bleeding from continuing by forming clots and protecting from blood loss. So we looked at this in lab. Again, the components of blood. This is the plasma, the liquid part of our blood. It's mostly water, but it's also made up of some other important things like antibodies, solutes, dissolved gases, proteins for clotting are the major components of plasma. There are others, but for our purposes, just know that it's the liquid part of blood. It contributes a lot to our blood volume. So if someone has low blood pressure, oftentimes we'll just give some normal saline to increase that plasma volume, and that'll increase their blood pressure. The erythrocytes, those are the red blood cells. Remember, that forms almost half of our blood volume is just red blood cells. That's the solid part of our blood, along with the buffy coat, this middle layer, which is made up of all these different white blood cells. And each of these white blood cells has a different function in terms of helping us with our immune function. And then the platelets, that's important for blood clotting. So we also find that in the buffy coat. So the important major function of red blood cells is to transport oxygen. So again, looking at plasma, it's mostly water. It's the liquid part of our blood. Has lots of different structures within, or substances within it. Lots of different substances. So when you donate plasma, you are helping primarily in this area, providing protein, clotting factors, and antibodies to those, patients who are lacking that. So we use your plasma mainly for these three things. But we won't go into the details of that and for our class. Just know, again, the plasma is a liquid part of blood and it contains lots of different substances, but we're not going to go into the details of those substances until you get into general or advanced A&P. So the red blood cell. If you look at a red blood cell, key characteristic of red blood cells is it does not have a nucleus, no nucleus. So we say it's biconcave, which means it kind of curves in on both sides. And we can see that here. It curves inward here and it curves inward here, biconcave. Think of what a sweet tart looks like. It's collapsed in the center, it's thinner in the center. That's what a red blood cell looks like, because when it doesn't have a nucleus, that plasma membrane sinks in the middle. And that makes it very efficient for traveling through the tiniest of capillaries, and these red blood cells can even fold over if necessary. So their primary job is to transport oxygen and also carries carbon dioxide between the tissues and the lungs. So not only oxygen does it carry, but it also plays a role in carrying carbon dioxide. And it contains hemoglobin, and hemoglobin is the special structure, the special protein that binds oxygen and carries it from the tissues to the blood and vice versa. Primarily blood to tissues, because we're unloading hemoglobin, unloading oxygen from hemoglobin from our blood to serve our tissues. Also contains lipids, ATP, and carbonic anhydrase, which helps in transporting carbon dioxide. Again, you'll learn more details on that in general or advanced A&P. So key functions is to transport oxygen and carbon dioxide, and it does not have a nucleus. When you talk about the term hemostasis, we're talking about the clotting factors present in plasma as well as the platelets that we see in the buffy coat. So hemostasis means stopping of bleeding, or the arrest of bleeding. It means you're stopping the blood flow when you have a break in tissues and in capillary walls. So the first thing that happens when a person would cut themselves, let's say you're slicing a tomato and you cut your finger, the first thing when that rapid loss of blood first occurs, the blood vessels that are losing that blood so rapidly spasm, which means they constrict, they narrow, and that's going to slow blood loss. So that's the number one thing that happens first off, is this reflexive vascular spasm. Then the tissue that is damaged on the edge of that capillary, just outside that capillary wall, releases factors that attracts platelets that are flowing by that area. So as the platelets present in the blood come in contact with the exposed tissue, those platelets stick to that exposed area, sticks to that broken blood vessel wall, and they start to release a chemical that attracts more platelets to stick. And as those platelets stick, they release chemicals that attract more platelets to stick. So it actually begins this positive feedback cycle of attracting platelets to that broken blood vessel wall. And then, if that is not enough to stop the bleeding, if you have more than a paper cut, for example, then the third step comes in, where we call that coagulation, or actual blood clotting. And that's multiple steps that lead to a formation of a blood clot. And that's, we can see just the general steps we just talked about, the spasm here, the platelet plug forming as platelets stick, and these platelets release chemicals that make more platelets stick. That's the positive feedback cycle. And then this coagulation, we have clotting factors in the plasma, we have clotting factors in the injured tissue outside of the capillary that's releasing chemicals, and also calcium and the enzyme thrombin and fibrinogen come in to form what we call a blood clot. So a blood clot is a mixture of fibrin and red blood cells and platelets that form a more long-term hole in that area until that area heals. So here's an example of what a blood clot would look like. This white fibrous tissue, this is called fibrin, and fibrin is made from fibrinogen. And if we go back and look at our plasma, we can see fibrinogen is an enzyme present in the plasma, and when it comes in contact with the enzymes present in the clotting process, that fibrinogen is converted to fibrin. And fibrin is an insoluble substance that is like a sticky fibrous web that attaches to the red blood cells and forms this clot. So clotting is a good thing when we want to stop bleeding, but when blood clots form inside of our blood vessels because we have high cholesterol and damage to blood vessels due to, say, lifelong or chronic smoking, then these blood clots form as a pathological process, and then that's what leads to heart attacks and stroke, when those clots get away from the area that they were formed and end up getting clogged into clogging a coronary artery or an artery in the brain, a cerebral artery. Then what happens after a couple days of this clot formation, we have another enzyme present in our blood called plasmon that is formed. It's not directly in our blood, but it's formed by a number of processes, and at the end of that is plasmon, which will dissolve these fibrin threads and dissolve that clot. So we do form little clots on a regular basis, but because of the activity of our fibrinolytic enzymes, of which plasmon is the final one, these clots break down, and then we continue on and we have no more trouble with clotting, in that area. And then a new clot may form somewhere else, but again, we're constantly breaking these down with the help of this final enzyme called plasmon. So just know that plasmon is something that dissolves a clot, breaks down that fibrin. There's other substances in our blood that also helps break down clots, and sometimes we have a patient that comes in with a heart attack or stroke, and we can give them a special drug that is a clot buster, and it comes from a bacteria, from the strep bacteria. It's called streptokinase, and that is something that we can give to patients to dissolve clots if we see they have symptoms of heart attack or stroke, and that can actually reverse the stroke. Heparin is an anti-clot medication. It doesn't break down existing clots, but it helps prevent the formation of new clots. So sometimes patients that tend to form clots, while they're in the hospital, they'll receive heparin injections to prevent new clots from forming. So when a clot is formed in a specific area and it's due to high cholesterol and damage to a blood vessel, we call that a thrombus. So a thrombus is any type of clot that is formed in a specific area. And then if that thrombus breaks away from that area and travels somewhere else, we call it an embolus. Common emboli that we see get trapped in the lungs and in the brain. Also can get caught in the heart, but a real popular one, if someone who's had surgery, say on their hip or their knee, they can end up with what's called a PE, which is called a pulmonary embolism, and that's a clot that has broken away from the surgical area and gotten caught in the lungs. And sometimes that can cause death, or it can just cause difficulty in breathing, and then they're going to give that patient heparin to prevent the clot from getting bigger, and then they're also going to give them maybe a clot busting medication, or just wait until that clot breaks down with the body's natural processes of that plasmin acting on the fibrin clot. So causes of blood clots, physical trauma, so car accidents, surgery can cause blood clots, severe burns, can cause tissue damage relating to clots, fatty deposits on the inside of our blood vessel walls, and sometimes just a sedentary lifestyle. People that sit like for long plane flights, they can end up getting a clot forming in their legs. So that's called a deep vein thrombosis, and that can be very serious. So that's why we want our patients to walk as much as possible after surgery to prevent the formation of clots. And that completes our discussion on the introduction to the cardiovascular system. The next video will talk about the topic of blood grouping and blood typing.